Good morning, or good afternoon, or good evening, depending on when you're listening to this. This is Dr. John giving the first lecture in the physics class for 2016-2017. I want to welcome you to this class. This introductory lecture is on the mathematics of physics. And what I want to do is go over the principles of how we do problems in physics and focusing on a couple of ideas that are important and will be important throughout your time in this class. One of those principles is the whole idea of units and how we work with units. The second is the idea or the distinction between accuracy and precision, and related to that is the idea of significant figures and how significant figures give an indication of the precision of a measurement and a result to a problem. And then finish up with a brief discussion of approximation. I thought this scripture was interesting. Actually, it's meant to be a joke, but it says, "It is good for me that I have been afflicted, that I might learn thy statutes." Many people see physics as an affliction. However, it is good that sometimes we are afflicted with these sorts of challenges, that we might learn the way God operates his universe. First of all, we have to start out with some definitions in the area of units and working with units. We apply units to various situations, and in order to do that, we have to understand what these situations are. The first of these is something we will work with from time to time, known as a model. You need to understand that when I talk about a model in class, I'm talking about a schematic representation of a process that is many times too difficult to demonstrate or display in real life. The important thing to understand about a model is it's artificial. It's not the way things really are. The problem is we probably don't know exactly how things really are. But in order to understand and put together the information we do know, sometimes we have to make up a representation of that process so that we can understand it. And it's important also to understand that we do this because otherwise we would not be able to do the demonstration or to display what we want to say. Now, this is in distinction to a theory. In a theory, what we do is we put together the information that we know based on observation and experimentation, and we put together an explanation for the patterns in nature that we see that are supported by the scientific evidence. And it's important to understand that for a theory to be accepted in science, it's generally been verified many times in various different groups and with various different research institutions. So you need to understand that when you say something is a theory, you're not in some way saying that it's unstable or that it's a possibility. It's a probability. Now, it's still falsifiable. Dr. Pop, who is a famous philosopher of science, defines science as a process that is falsifiable. That means that it's possible to find evidence that will falsify whatever you believe. And a theory is falsifiable, but it does not mean that it's not probably true. The reason I'm emphasizing this is many times people talk about the theory of evolution and think because it's called a theory, that means it's not well supported. That nothing could be farther from the truth. They also talk about the theory of relativity, and virtually all scientists believe that relativity is true. So I strongly recommend not getting into that argument where you say, well, it's only a theory. A theory is supported by a very strong amount of evidence in general. Now, on the other hand, a law is something that is a concise description, generally and many times using mathematical formulas, for a pattern in nature that has been shown in repeated experiments. So, for example, the law of gravity has been shown to occur over and over and over and over again. Now, I am not going to get into the problems of induction, but again, even with a law, it is possible to falsify a law. And so both theories and laws can be falsified and can be questioned. Most of Newton's laws relative to space and time, etc., have been generally falsified by the laws that have been generated through the theory of relativity. And so even those laws that seem to be fairly stable, they can be falsified. And even laws that have been falsified, such as many of Newton's laws, are still used because they explain 99.99% of the things that happen in our universe, and are only falsified at very extreme circumstances. So here's an example of a model. This is the planetary model of an atom, and generally this was generated to help people understand the information that we knew about atoms, electrons and protons and neutrons. It's a mental image of an atom. We cannot see an atom directly, and it shows the nucleus as the center and the electrons as flying around, like orbiting the nucleus, much like the sun being in the center and the planets rotating around the sun, or a planet being the sun center and the moons around that planet being those particles that fly around the outside. So this is an example of a model. Models are very useful, but cannot be taken as the absolute gospel truth, because remember, they are artificial generations based on the data that we have. Now, I cannot overemphasize what I'm getting ready to talk about in terms of units. It is extraordinarily important for people to understand what units are and how to use units. And again, we have to start with some definitions. The units that have been accepted worldwide are known as SI units. Now, SI stands for System International. The System International was developed in order to standardize units across the world. As you probably well know, there are various unit systems out there. And in order to try to standardize units, the Systems International was developed. The 6 fundamental units of the System International are shown in this slide: the meter, the kilogram, the second, the liter, the ampere, and the candela. All of these measure different aspects of the universe. The meter is length, the kilogram is mass, the second is time, the liter is volume, the ampere is current, electrical current, and the candela is light intensity. Fundamental units are basic. In other words, they're not derived, and we'll talk about what the difference between fundamental and derived units here in just a moment. The English unit system is the unit system in Britain and the US. The metric unit system is generally used in the remainder of the world. The SI unit system is foundationally based on the metric system. The US, as you can see, the same 6 parameters in the U.S. or English system are shown here, and you can see there is some of those units that are the same and then others that are different. Now, derived units are units that are produced by a combination of fundamental units. For example, the acceleration, which is the increase in velocity divided by the time it takes to increase the velocity, and then velocity being the distance covered over time. So if we start with velocity, that's a derived unit, and it's a length divided by time. So it's meters per second or yards per second. And then acceleration is velocity over a period of time, so then it becomes meters per second or meters per second squared. And then we get to the units that I've shown here, the Newton being the mass times acceleration, a unit of force. And its mass kilograms times meters per second squared, or the Joule, which is force over distance, so it's kilograms, so mass times meters, distance times acceleration, meters per second squared. So the derived units are all derived from fundamental units, are all produced from fundamental units. Now this last statement is the most important statement that I'll make about units. Always label your answer with units. I will take off if answers are given on quizzes or tests or homework that do not have units. So it is extremely important, because an answer without units is useless, as this next slide shows. In this case, a unit has been given, but the poor observer here doesn't know what it means. He's thinking, what's a cable? Or how long is a cable? So in order for this to be useful, you have to have some sort of way of translating cable into meters, which is the System International unit for length. So distance given in unknown units is maddeningly useless. A distance given without units is even more maddeningly useless. Now, fundamental units have very specific and interesting definitions. For example, the meter is defined as the distance light travels in a very short period of time, shown on this slide, in a vacuum, because the speed of light is mildly different in a vacuum versus in other media. This distance then can be multiplied by time in order to show the velocity, or to come back to the velocity of light. So what you see here is a very fundamental definition of a fundamental unit. They define a second in terms of the oscillation or the vibration of a specific atom in a specific environment. And so these fundamental units have very specific objective definitions. Now, we're going to talk about something called dimensional analysis. And dimensional analysis is a very important way of using units and converting from one unit to another unit. And we're going to do a couple problems here in order to discuss this. Dimensional analysis is just a fancy word for how we change from one unit to another. And you can see here is a problem. It says a light year is the distance that light can travel in 1 year expressed in miles. If the distance, excuse me, if the speed of light is 300 million meters per second, how far is 1 light year in miles? Okay, so how far can light travel in 1 year in miles? And so we're going to use dimensional analysis to convert this, and I've given you the one number that you have to know in order to do this, that we can travel 300 million, my handwriting's not so good, meters in a second. Now, we can either first convert seconds to years, or conversely, we can convert meters to miles first, and then seconds to years. So let's start with the meters to miles. Remember, there were 1,609.334 meters in 1 mile. Now, the reason I wrote it this way is you can then cancel these 2 meters out. And what I've done is convert this meters to miles per second. Okay? And then after that, what we have to do is convert seconds to years. And so we have 3,600 seconds, and that's 60 seconds in a minute and 60 minutes in an hour. So that's 1 hour. And then there's 24 hours in 1 day, and 365.25 days in 1 year. 8 times 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So a light year is 5.88 times 10 to the 12th miles. That's the distance light travels in 1 year. And this is called dimensional analysis, where and the dimensional analysis part is where we take all these various dimensions or units and we can cancel out each one until we're left with miles on the top and years on the bottom. And so that's how far light travels in 1 year. Now, for just interest's sake, what was the other problem here? Let me move this over for just a second. Let's say the average person weighs 160 pounds. What is that person's weight in kilograms? Okay. And the conversion factor I gave you is 0.4536. So 160 pounds, and it's 0.4536 kilograms in 1 pound. So how do we do this? Well, now we can get rid of the pounds here. So now we know 160 pounds. If we multiply these two numbers, that we'll know how many kilograms that is. Well, 1 kilogram is 1,000 grams. Kilogram means 1,000 grams. And 1 gram is 1,000 milligrams. This one, we get 7.26 times 10, 3, 4, 5, 6, 7 to the 7 milligrams. So we've converted 160 pounds to 7.26 times 10 to the 7th milligrams. So that's converting units using dimensional analysis. Move on with some new definitions. What we just worked with is known as a conversion factor. A conversion factor is a ratio that relates one unit magnitude to a similar, and that's important that it's a similar unit magnitude. For example, in this case, you see that we're converting one length, the meter, into another length, the centimeter. And this conversion tells you how many centimeters are in a meter, and you can invert this in such a way as to show how many meters are in a centimeter. Now, the second thing I told you we were going to review in general was the idea of accuracy. Accuracy and precision are two ideas that we have to be distinguished, because we're going to be talking about significant figures here in just a minute, and significant figures are a measure of precision and not accuracy. Accuracy is the degree to which a measured value agrees with the truth. So, for example, in God's mind, you have a certain weight, say 160 pounds, and that's the real true value for that weight or mass. Accuracy is the degree to which your scale, your measuring device, agrees with that true value. On the other hand, precision is the degree to which repeated measurements agree with each other. Notice it doesn't have anything to do with the true value. So a measuring device can be extremely precise and inaccurate at the same time, or can be accurate but imprecise. And so it's important to understand the difference between these two, because when we talk about significant figures, we're talking about something that expresses precision, not that expresses accuracy. And it's very important to understand that you need to make sure you express your results with the proper degree of precision based on the precision of the measurements, and understanding the definition of precision when I use it there. So here's an example of a precise measurement that's inaccurate. You see here that the dots are concentrated very close to each other. So repeated measurements or repeated actions that are very close to each other. That is highly precise, or has a high precision. However, they're not very close to the bullseye, and so the accuracy is low. Conversely, if you're trying to hit a bullseye, in this case they talk about a GPS system trying to locate a restaurant, in the center would be the bullseye. The black dots represent each indication of where the restaurant is, or each shot at the bullseye. You notice the dots are very far from each other, but they're reasonably close to the bullseye. So they have low precision but fairly high accuracy. Now, significant figures are a measure of precision and not accuracy. So as we go through the rules for significant figures, we have to remember that we are trying to retain the precision of the measurements in the answers that we give. The key thing to remember is the precision of your answer cannot be greater than the least precise measurement. And so the number of significant figures of an answer cannot be greater than the number of significant figures in the least precise measurement, or the measurement that has the lowest number of significant figures. So that's why we're going through all these rules, is so as you do problems, you understand how to express the answer in the proper precision. First of all, it's very simple. Any non-zero number is significant. Now, where things become exciting is when we talk about zeros. If you put a zero between two non-zero numbers, it's significant. So for example, in these cases, the 4 and the 5 are significant because they're non-zero numbers. The 0 in between is significant. The 6 and the 2 in the 6002 here is significant. Therefore, the 2 zeros in between are also significant. The next example has both significant and non-significant zeros in it. The 3 zeros between 1 and 3 are significant because they are between 1 and 3. But the other zeros here are not. And so this number has 5 significant figures. Zeros at the end of the number, extremely important, with a decimal is significant. At the end of a number with a decimal are significant. And so here we have 3 zeros at the end of this 14. There's a decimal here, and so those 3 zeros are all significant. The next one shows 2 significant zeros and 1 non-significant zero. The first 0 is not at the end, and so it's still not significant. But the other 2 are at the end, and there is a decimal present, and so they are significant. Zeros at the end of a number without a decimal are not significant. And these examples, the first one, there are 3 zeros, but there's no decimal, and so you have 1 significant figure here, 2 for the next one, and 2 for the next one. Now, if you wanted to show that any of these zeros were significant, all you would have to do is put a decimal at the end where the commas are in the first 2. And if you put a decimal there, then suddenly those zeros become significant. Now, another way to think about this as we go to the problems is if the 0 is functioning only as a placeholder, then it is not significant. However, if it is functioning to show that the measuring device is saying 0 instead of some other number, then it is significant. So if we go back, if you look at the bottom examples, those zeros are only placeholders. In the first case, to show that the 4 is in the thousandth place, it's just those 3 zeros are just a placeholder, and so they're not significant. The same is true for the others. But if you move up to the next example, 14.000, those zeros are to show that in the 10th place we have a 0 instead of a 1 or a 2. In the 100th place we have a 0 instead of a 1 or a 2. And in the 1000th place we actually know that that's supposed to be a 0 instead of a 1 or 2. If the device did not measure to that degree, you would just leave that blank and not put anything there. So let's look at our problems. For each of the following numbers, give the number of significant figures. The answer here is 3. The first 0 is just a placeholder. It's not at the end of a number, it's at the beginning, and so the fact that there's a decimal doesn't matter. So that first 0 is not significant, but the second one, which is between 2 non-zero numbers, is significant. So 3 significant figures here. This is very similar to what I showed you as an example. These 2 zeros are at the end of a number without a decimal, so they're not significant. These 2 zeros are placeholders, so they're not significant. So there's 2 significant figures in this number. The answer here is 5. The 0 is between 2 non-zero numbers, and so it is significant. So there are 5 significant figures in this number. Okay, we have 4 zeros here, but there are only 3 significant figures. The 2 non-zero numbers obviously are significant. We have a decimal, so the 0 at the end is also significant. But the other 3 are not at the end, and so they're not significant. They are also placeholders, so they're not significant. Now, what's more important here is the fact that when we give an answer after we do a calculation, we have to express the answer properly in terms of its precision. Therefore, we have to express the answer in the proper number of significant figures. So for multiplication and division, the rule is as follows. You round the answer. That means you re-express the answer to the factor with the smallest number of significant figures. So in your measurements, whichever one has the least precision and thus the smallest number of significant figures, the answer is controlled by that factor. And so whichever one that is, the answer is going to have the same number of significant figures as that measurement. For addition and subtraction, you round the answer to the place which has the greatest uncertainty. And I'll show you what that means in these examples that are coming up. So let's look first at this first problem. So we have 3.609 times 12. All right, let's look at 3.609 times 12. How many significant figures are here? Answer that in your head. It's 2. And here, this is between two non-zero numbers, so this 0 is significant, so there are 4. 4 versus 2, so the answer can have no more than 2 significant figures. And the answer here is, on your calculator, is 43.308. So your answer, as printed out on your calculator, has 5 significant digits. However, we just said that you can only have 2. This is the smallest number, so you have to get rid of these. So your answer is either going to be 43 or 44. And since this is less than 5, less than half, you would round down. And so the answer is 43. 1001 plus 23.981. Okay. Now it's best to write these addition and subtraction this way. Let me look at that again, 981. And our answer is going to be 4.981. Now, the greatest uncertainty here is the last one we know is the ones place. This is where the uncertainty for this measurement starts. And so it controls the answer, the precision of the answer. The precision here is to the ones place. The precision here is to the thousandth place. The least precise is this 1001, and so you have to move it down here. And this number is greater than 5, and so the answer is going to be 1025. And you don't have to put a decimal there because this is between two non-zeros. So you see you have 5 and 4 here, and just in this case it just so happens that this is 4 and this is 4. But if this would have been 981, it would have still been to this place. Okay? Let me show you what I meant by that. Let's say it's 981 plus 23.981. Again, we have 81940. Okay, so there's your answer. again, its uncertainty begins at the tens place in this number, okay? This spot right here. And so, again, you would eliminate this, and it would be 1,005. You know, this has 3 significant digits, so unlike here where it would be 3, the answer has 4. But the uncertainty begins at the tens place, so that's why we have this. Let's look at another one. We've got 45.3 divided by 9.0342. So 45.3 divided by 9.0342. You get 5.01427991. Okay? This has 5 significant digits. 1, 2, 3, 4, 5. This has 3. So this is the controlling factor. So your answer has to stop at 3, which means you got to get rid of the rest of this. Since this is less than 5, you round down to 5.01. One more. 45.1 minus 22.9823. 45.1 minus 22.9823. So we're subtracting here, so that's 7, 7, 1, 0 is 1, 2, 2. Again, your uncertainty begins right here. So you need to get rid of this. And so this is less than 5, so the answer is 22.1 in the proper number of significant digits. Now, if you have any questions about this, you can bring them up in class. Approximations. We don't do a lot of approximations in class. However, I recommend thinking about this because doing approximations helps you when you get an answer to understand if your answer makes sense. And if your answer doesn't make sense, then you know you made a mistake and you need to go back and correct your mistake. So let's take a look at how to do approximations. Approximation is an estimated value based on prior experience and reasoning. Let me give you an example. So first of all, you select a value with which you're relatively familiar. So let's say you know that the average person's height or an average person's weight. Then you relate that value to something unfamiliar with a reasonable ratio. So for example, if you're trying to estimate the weight of a gorilla, you would say that gorilla is about 3 times as big as a person. You know that a person weighs a certain amount, and you use that relationship to estimate the weight of the gorilla. So the gorilla is about 3 times as big as a person, and people weigh about 170 pounds, and so that gorilla must weigh about 500 pounds. So that's how we do approximations. If you look at this example, a bank stack contains 100 $100 bills. 100 times 100 is 10,000. How many stacks would make up $1 trillion? Now, $1 trillion, another way to do this, by the way, in this situation is to look at scientific notation. So let's look at a scientific notation. 10,000 is 10 to the 4th. It's 10 express 1, 2, 3, 4. So it's 1 times 10 to the 4th, or 10 to the 4th. A trillion, which I'm not going to write up here, I'll just tell you, is 10 to the 12th. Okay. So how many stacks, if there are X number of stacks, and they're each contain 10 to the 4th, how many stacks would it take to get to 10 to the 12th? So X would be 10 to the 12th divided by 10 to the 4th. When you divide, you subtract the exponents. So 4 subtracted from 12 is 8. So it would take 10 to the 8th stacks. Now 10 to the 9th stacks is a billion. So 10 to the 8th stacks is 100 million. So 100 million stacks would be required in order to have... So we finished our slides here, and I would say that once you go through the homework, if you have any questions, please feel free to bring them to class on Monday, and we will go over those questions. I will also, if their time permits, give you more examples. And the first quiz will cover these principles of approximation. There's one other thing I wanted to show you about using approximation. Let's take a look at some of these things we calculated here. For example, look at this example right here. This is approximately 45 divided by 9. Now what's 45 divided by 10? See, in order to do an approximation, what I do is pick a division that's easy to do in your head. 45 divided by 10, so we're going to say 45 divided by 10 is going to equal 4.5, right? So your answer, 5.1, should be pretty close and a little bigger, since it's divided by 9 instead of 10, than your approximation, 4.5, which is exactly what you got. Now, if in your answer you got 2.63, you'd know these are not very close together, and this 2.63 is in the wrong direction, so you'd know that there was a problem here. If we looked at, say, this up here, if you said 160 times a half would be about 80, and then times 10 to the 6th, 80 times 10 to the 6th, or 8 times 10 to the 7th would be an approximation. Again, your answer should be fairly close to that, and if you didn't get that, comparing these two answers, then you know you made a mistake and you need to go back and fix it. Just a little sidelight about how we can go about doing this. So with that, I'm going to wish you good luck on your homework problems and on the quiz coming up.